In this video, I will go through how to compare multiple study group means using R. The data that I'll be using can be downloaded by following the link at the top of this script. And I'd like to begin by giving a brief explanation about how this fictional data set was generated. An experiment was run to determine whether consuming a ketone-containing drink lowers blood glucose and non-esterified fatty acids, abbreviated to NEFA. 20 participants were recruited to a matched group design, random order controlled study. So 10 participants per group, and they were assigned to those groups in a random order. A baseline blood sample was taken, represented in the dataset by 0 minutes, and participants then consumed a ketone-containing drink or a control drink. Further blood measurements were taken at 30 minutes, 60 minutes, and 90 minutes while the participant rested. The experiment has two independent variables: condition, which has 2 levels, ketone, and control, and time, which has 4 levels: 0 minutes or baseline, 30 minutes, 60 minutes, and 90 minutes. This vignette will go through the process of visualizing data using line plots, parametric assumption testing, performing a two-way ANOVA with or without repeated measures, and post-hoc tests. We'll begin by installing and loading the packages needed for this session. And those packages are R Markdown, Knitter, ggplot2, ggpubr, dplyr, rstatistics, and emeans. Now, a quick note about the R Markdown package. So this script is presented using R Markdown rather than the normal R script. To create an R Markdown document, you just go to the top, File, New, and choose R Markdown rather than R script. Now, the benefits of using R Markdown won't be discussed here, but for now you just need to know that the code is surrounded, so you can create code chunks, as they're referred to, and they're highlighted by these grey boxes. And these code chunks are contained using these 3 dashes at the top, and those you can find that on the same key on your keyboard as the tilde, and it's followed by the curly brackets with an R in there. Forget the message equals false here. And at the end of the code chunk you have a further 3 dashes. Now, one of the benefits of using R Markdown is that you can run the entire code chunk as one by selecting the green arrow over at the side. Also on this link, by following this link, you'll be able to download the script both in as an R Markdown script and also as a more traditional R script. Okay, so you'll notice that we're using, rather than the traditional install.packages function, we're using that but containing it within an if-else statement. So what this is saying is, if the required package is not installed, then install the required package. So if the required package, in this case R Markdown, is not represented by the exclamation mark installed, then install R Markdown. And the benefit of doing this is that you'll quite often use the same packages on different scripts, and those packages previously been installed. So rather than having to reinstall the package every time, this will, in containing this within an if else statement, will mean it will only install it if necessary. And then we'll use the library function to actually access these from our library. Alternatively, you can go over to packages and put a tick next to the packages you want. We now need to make sure that our working directory is set correctly. To do that, go to Session, Set Working Directory and choose Directory, and that'll be the directory that you saved the .csv file downloaded by following this link to. Then we need to load the .csv file from your working directory and assign it in this case to an object called ketone. Now to do that, we use the read.csv function with the name of the .csv file with exclamation marks either side and contained within parentheses, and assign it using the arrow to an object called ketone. So if you run that, and now let's look at the structure of the data frame using the structure function. So we see that the data frame in question has 80 observations of 8 variables, and those variables are ID, so that's a participant ID, condition, whether it's ketone or control, body mass. Notice that there are NAs included within the body mass factor, because body mass was only measured at baseline, not at subsequent time points. Time, which is, as we said before, has 4 levels, so 0 minutes or baseline, 30 minutes, 60 minutes and 90 minutes. Gender, male or female, and then we have beta-hydroxybutyrate, shortened to BHB, and this is a type of ketone body and the one that we'll be measuring, or we did measure. And then we have our 2 dependent variables, glucose and NEFA. Now within this example we're actually going to be focusing only on the glucose dependent variable. And notice also here we get some information about how R has decided to, or interpreted, that the data should be the type of data contained within each of these factors. So you'll notice here that it has assigned ID, condition and time to integer, character and integer respectively. But these are actually nominal data, and so we need to change them to factors to save them as factors within this data frame called ketone. Also, it would be useful if we could change the names applied for time to baseline, 30 minutes, 60 minutes and 90 minutes. And the reason for doing that is those will obviously be categories when we come to plot this data using a line plot, and it will look a lot more intuitive if we have those listed as time points and baseline. So to do that, we're going to use the factor function. So let's break this code down. So we have over here on the right hand side, so we've got ketone is the name of our data frame, and time in this case is the factor within the ketone data frame that we want to change or alter. And we use this $sign here to identify that this is a factor within this data frame. So if you come back to the report we got from the structure function, you'll notice that each of these variables or factors has a $sign in front of it. So what we're saying here is ketone, name of the data frame, $sign, and then a factor name. So going down here, we've got our levels as they currently are. So the levels here, and this is the combine function, so C with parentheses is used to combine variables or data. And so currently we've got them set as 0, 30, 60 and 90, but instead we want to apply labels. So again, we're using the combine function, and I will interpret this that we want to replace 0 for baseline, 30 for 30 minutes, 60 for 60 minutes, and 90 for 90 minutes. And then if we come back up, we are then, because we want to convert this to a factor, we're using the factor function, and we're assigning this back to ketone $time. So we're assigning it back to itself. And then we're going to do similarly with the condition factor. So we've got ketone, the name of our data frame, $ condition. And here we're just, because we don't need to change the naming convention within the data frame, we're just going to use the factor function to change this to a factor and assign it back to itself. And then finally the same again with ID. So if we run that, and you'll see we get a little green bar on the side here telling its progress through running it. It's very quick. And now we can check to see if this has worked. So if we run the structure function again, and now we should see that ID is saved as a factor, condition is a factor, and time is a factor. And it's really important that we do this before going on to perform any analyses, because otherwise the two-way ANOVA simply wouldn't work. Okay, so we're now going to visualize the data, and probably the best way, given that we've got multiple levels of time, probably the best way of doing this is to use a line graph. And for this, we're going to use the ggline function within the ggpubr package. This could be done in ggplot2, but my preference is using ggline. The ggpubr package. Okay, so let's break this code down. So if you're familiar with ggplot2, then the conventions are very similar. Here we're assigning this to an object called glue_line, assign with the arrow. And we've got ggline is the function. We've got ketone here, which is our data frame. We're saying that we want time on the x-axis. We want glucose on the y-axis. And we're going to change the color based on the condition. In other words, that the color that's presented on the graphs will be different for each condition, either ketone or control. And we're going to add, and using the combine function here again, mean and standard error. And we're going to also plot all the individual time points on there, and we're going to use the jitter function to do that. We're choosing a particular color palette. In this case, it's Lancet color palette. And we're applying labels to it. So the x-axis label will be time with minutes in parentheses, and the y-axis label will be glucose with millimoles per liter in parentheses. And then finally, we're going to print the glue line object that we just created. So let's run this. And there we have it. So automatically we can tell that there are some clear differences between the conditions here. And if we just apply the code we just wrote to this graph, we can see that, so we've got glucose on our y-axis, it's labeled correctly, we've got time, and notice here, so this is what I meant before about changing the labels for time. It suddenly looks better and it's easier to interpret, having baseline 30 minutes, 60 minutes and 90 minutes here. And we've got time as our label for the x-axis. We have our jittered points, and at each time for each condition we have a mean plus standard error presented. So having inspected the data and also visualized the data using a line plot, we're now going to move on to performing some parametric assumption testing. And to begin with, we'll check to see if there are any outliers within the glucose variable. To do this, we're going to use the group by function, which is part of the dplyr package or dplyr package. Now, this is an extremely useful package which provides a set of verbs such as mutate, select, summarize, arrange, filter, and in this case group by, which allow you to manipulate data frames, and we'll see some examples of that shortly. And we're also going to use, or we're going to combine this with the identify outliers function, which is part of the R statistics package that we previously installed and loaded. So let's look at the code. So we have a data frame here called ketone. This is called a pipe. And again, this is part of the functionality of the Deepler package. And what this tells us, or tells R, is that everything to the right of this pipe will apply to what's on the left. So in this case, we've got our data frame ketone, the pipe, and that means that everything here applies to the ketone data frame. And by doing this, it means that we don't need to type out the ketone $$ each time, because we've already said that this is related to the ketone data frame. Okay, we have a group by function, and we're going to group the results based on condition and time, our two dependent variables. And then we have another pipe here. And then finally the identify underscore outliers function with just the variable that we're interested in within parentheses. So let's run that. And we can see that it has identified one outlier. So it gives you a report and says, is outlier, in this case true, is extreme outlier false. So we might want to go back and look at our line plot to determine whether this is really an outlier or not. So if we look here, we've got control 60 minutes and the glucose is 4.4. So control is the blue, 4.4, 60 minutes. So it's this point here, and this isn't really an outlier. An outlier being defined as a true outlier being defined as a result of experimental error. In reality, I think this is more to do with biological variability. And if we want to know, so in this case, I'd make the call to keep that within our data frame or data set. And if we want to know how outliers are defined, we can use the help function to get a help about the package or the function that we're using. So if we run this, we should find over here in the help window, here we go, scroll to the top, and here we go. So it tells you exactly how they're actually defining the outliers, and they're using interquartile ranges. But as I say, I don't consider this to be a true outlier, so we'll move on without excluding that from our data set. So the next assumption test that we'll cover is, are the observations independent? And yes, we don't need to perform any tests to determine this. We know that the participants were randomly assigned to the groups, and it's a matched group design. In other words, the participants didn't do both conditions of the study. They only performed one of the study conditions. So we can move on from there. Is the data normally distributed? And a good way of doing this, so in fact we'll test this in a couple of ways. We'll begin by creating a QQ plot, and we'll do that for each condition at each level of time, and it will become clearer what we mean by that in a second. So for this, we're going to use the ggqqplot plot function, and this again is part of the ggpubr package. And we're also going to use the facet grid function, and this is part of the ggplot2 package. So let's go down to the code. Firstly, we're going to assign it to an object called glue_QQ. And obviously we have our arrow telling us that this is being assigned. Everything on the right of the arrow is being assigned to this object name. Just a word on the object names. It's important to try and keep them consistent and intuitive. Also, probably bad practice here that I have a capital G at the beginning. It's best, given that R is case sensitive, it's probably best to keep things lowercase, and you could argue the same applies for the QQ. Okay, so we have a ggqqplot plot function. Ketone, again, is our data frame, and on the x-axis we'll be plotting glucose. Colour equals condition. So as with before, the colours will be different depending upon the condition. And here, instead of using the, if we look at the code above, on this one we used a palette theme, which was called Lancet. Here I've actually specified specific colours using using hexadecimal colour coordinates. And if you search for hexadecimal colours or colour charts, then you'll be presented with hundreds of different colours, each of which have a unique code that you can enter if there's a particular colour you would like to apply to a graph. Okay, so we've also got a plus here because we're also then adding a facet grid, and this will, in fact, let's run the code and then explain what this facet grid does. There we go. So remember, we said that we're going to create QQ plots for each condition at each level of time, and that's what we've got here. So we've got columns, we've got control and ketone, and then our rows, we have baseline, 30 minutes, 60 minutes, and 90 minutes. And to achieve this, this is where the facet grid comes in. So we have time, i.e. baseline 30, 60, and 90, as a function of condition, and the labeler equals label both, so it's just saying that it's going to apply a label to both the rows and the columns there. Now if we switch these two around, in fact let's do that. So if we have condition and tilde and time, and run that again, there we go. So you see it switches it round this time. So whatever is before the tilde will go as the rows, and whatever is after the tilde will go as the columns. Yes, I think either way is fine. So we can say that the points roughly fall along the reference line, so we may assume that they are normally distributed, although you can see there are examples where this isn't necessarily the case. So perhaps what we would want to do in this situation is actually perform a Shapiro-Wilk test to statistically determine, or in other words, assign a p-value to whether the data is normally distributed in each condition for each level of time. Okay, so let's look at that code. So again, we have a keto data frame. We have the pipe function as part of the deepler package. So everything after this pipe will apply to ketone. We're again using group by and condition and time. And then we have our pipe function again. And then finally, very simply, Shapiro underscore test and the variable we're interested in, which is glucose. So let's run that. And here, this gives a better example of using the group by condition and time. So here we can see it's condition, it's grouped it by, and then time, it's grouped it by as well. Okay, so moving on to our p-values. So none of those p-values are below 0.5. Put another way, all of them are above 0.05. So we may proceed. So the final parametric assumption test that we're going to perform is to determine whether there's homogeneity of variance. And for this we will use the Bartlett test. And intuitively this is a function called Bartlett.test and is part of the preloaded statistics package. So you don't need to install anything or load anything to access this particular function. And very similar to the other functions or chunks of code that we've been running, here we have the function name, so Bartlett.test. Here we have glucose as a function of, and now we have the interaction between condition and time. And this reflects that this is a two-way ANOVA, or we'll be coming on to, this reflects that there are two dependent variables within this data set, both condition and time, as discussed at the very beginning. And then in this case, we have the way we assign the data frame to it is with data equals ketone at the end. So small variances, but the same sort of principle to each line of code. And if you want to understand what arguments need to go into a particular function, for example, the Bartlett.test, then if you just run the question mark Bartlett.test, and then there we go. So we get information here about the arguments that it needs to contain. If sometimes I find that is not always the most helpful information, and actually you might be better off just searching online, and no doubt you'll find the answer you're looking for. Okay, so let's run this. Okay, so Bartlett test of homogeneity of variances, and here we can see the important value there is our p-value, so it's greater than 0.05. So having passed the parametric assumption tests, we can now go on to perform a two-way ANOVA. And this, of course, is a two-way ANOVA because we have two dependent variables that we're interested in. And with that in mind, let's think about what the question is. Does blood glucose concentration depend on the study condition, ketone versus control, and /or time, being baseline 30 minutes, 60 minutes, and 90 minutes. And this /or is important because we're also interested in the interaction effect between condition and time. So to perform the two-way ANOVA, we can use the analysis of variance function, or AOV function, which is part of the preloaded statistics package. But before we do that, there's a couple of things we need to check first. Firstly, we need to know whether the data is in long format. Now what we mean by this, in fact, before I do that, let's run the head function, so head with ketone in parentheses, as we did before, just to get the top 6 entries of the ketone data frame. So what we mean by long format is that the repeated measures for each individual are in rows, and that is the case here. So for participant number 1, part of the ketone group, you can see that the baseline 30, 60 and 90 minute measures are in rows. So if this was in wide format, it would mean that each level of time would be across the top in columns. So if that is the case, if you do have a data set that is in wide format, you need to convert it to long format, which is easily enough done within R, although that's not covered in this tutorial. Okay, so we can move on from this as we're satisfied that it is in long format. And the second point is, have the variables, in this case participant ID, condition and time, being converted to factors. Now you remember that we did this at the beginning, but it's sensible just to double check because this would adversely impact the two-way ANOVA. So let's run the structure function again just to double check this. So we've got ID, condition and time are all listed as factor variables because they are nominal data, so that is fine. So yes for both, and we can proceed. So as mentioned, we'll be using the AOV function, or analysis of variance function, which is part of the preloaded statistics package. And you'll notice some similarities between the format for this and with, for example, the Bartlett test that we just performed. So here we're going to assign this analysis of variance to an object called glue_to_ANOVA. So you'll notice I mentioned before about being careful with capitalizing letters or object names, etc. So here is an example how I've not been consistent. I've got glue as undercase there, but I'm pretty sure earlier on when I created, here we go. So here I created a QQ plot, saved it to glue_QQ, but I used a capital G, and that isn't great practice because that will catch you out at some point. Best to stay consistent throughout. Okay, moving back to our ANOVA. So let's break down this code. So we're assigning the following to glue_2 ANOVA. We've got our analysis of variance function, and then in parentheses we've got glucose as a function of, represented by the tilde, condition times by time. So this is the interaction term that we're interested in, and this is what sets this out as a two-way ANOVA rather than a one-way ANOVA. So if we only had one dependent variable, we wouldn't have, we would, for example, just have glucose as a function of condition. But here we have two dependent variables, and we're interested in the interaction between these as well as individually their effects on glucose. So you'll notice that we came across this in the Bartlett test earlier as well. Here, instead of having using the multiplication sign, we specifically said interaction and then had parentheses with condition and time in there. So the different functions do sometimes require different ways of expressing the same thing. So again, if you're in doubt, then you can refer back to or you can use the help function to understand what it is expecting in the arguments for each function, or better still, go online and have a search. Okay, so and then here we've got data equals ketone again, so this is referring us back to our data frame. And then importantly, rather than just simply printing glue_2 ANOVA, the object, if we did that, we get some information about the model, some model statistic information, and that's okay, but really what we want is to use the summary function, and that will give us the values we're interested in. So let's run this chunk of code, and so we can see here that we have all the data we would need. We've got our condition dependent variable, time, and here we have our interaction between them. And if we look, we've got the degrees of freedom, we've got our F statistic, and importantly at the end there we also have our P statistic or P value, and we can see, so it helpfully gives us stars and gives us a little legend at the bottom telling us, although we can actually just read off directly here, we can see that both condition and the interaction term between condition and time are both significant. So in summary, there is significant ANOVA effect of condition on blood glucose concentration. Additionally, the effect of condition on blood glucose concentrations depends on time, which we may have predicted if we go back to the line graph we created. So intuitively, that's what we would have said. There seems to be a difference between conditions, but that does seem to depend on time, and that's largely because we had this baseline pre-drink value where the glucose levels were more or less identical before diverging after having the drink. Okay, so a little note here. So we this study design was a matched group study design. So participants were recruited and completed one arm of the study or one study condition only. Now, if it was the case that we recruited participants into a crossover design study where they, in a random order, completed both study conditions, then we would need to perform a repeated measures two-way ANOVA. And that is very simple to do. All we need to do, so we take the code that we created above, but we add an error value for each participant within the model. Having identified that there's an interaction effect between our two dependent variables, condition and time, for our independent variable, glucose, we would want to go on to perform some post-hoc tests to try and determine at what level of time that effect occurs. Or put another way, we'll try and analyse the effective condition on blood glucose concentration at every level of time. Let's just illustrate that using the line plot that we created earlier. So we're interested in understanding whether the blue and red dots are different at each level of time. So baseline 30, 60 and 90 minutes. Intuitively, we can probably guess where that is, but obviously we need to formalize that by doing some post-hoc testing. And to do that, we're going to use the e-means package. Now, there are other ways of doing post-hoc testing. Indeed, there are other ways and functions that can be used to do almost all of what we've covered in this tutorial, but the e-means package is one that I enjoy using, and so hence why we're using it here. So here we're going to create a glue_post1 object, and to that we're going to assign using the e-means function. So notice here, before, in all other steps we've been referring back to the ketone data set, but what we're actually looking at now is the linear model that we created when we performed our analysis of variance. So that's what the glue_2 ANOVA is, the linear model. And this argument here is telling us, or telling R, that we want to do pairwise comparisons between condition and time. So just going back to our line graph, so we want to do pairwise comparisons between condition at every level of time. And then finally, the type of post-hoc test that we're going to use here is the Tukey test. So let's run this chunk of code, and there we have it. So we have our pairwise comparisons between control and ketone at each level of time. And we can see, if we go down to the second part of this, which gives us our p-values, that as we would have predicted, I'm sure, that there was no difference at baseline. Intuitively, that should be right. This is pre-drink. But at 30, 60 and 90 minutes, the comparison between the two groups was significant, or they were significantly different. So final thing to note is that the e-means package automatically adjusts for multiple comparisons. And there we have it. So relatively quickly we've gone through how to visualize data using line plots, parametric assumption testing, performing a two-way ANOVA with or without repeated measures, and post-hoc tests.